Welcome to Kairos Research Center podcast. Christian faith seeking understanding, intellectual witness, and spiritual renewal.
The multiverse theory explained that there are many universes beyond what we can observe, thus increasing the chance of a fine-tuned universe. Why is this not a viable option coming? The multiverse theory explains that there are other universes beyond what we can observe, thus increasing the chances of fine-tuned universe. So meaning the odds are in this favor to have a fine-tuned universe. So why is this not a viable option in your view, coming?
Well, what is multiverse? Multiverse means, in a way, to say that in addition to the universe that we know, that we can observe, there are other universes. Not only just other universes, infinite number of other universes. Because you must postulate an infinite number in order to arrive at the very possibility of the low impossibility of life.
Okay, maybe I jump in. Isn't this very ad hoc? I mean, this kind of theory.
Of course, I mean, I will explain why the unbeliever at the end of our discussion resort to what I describe as desperate expedient.
Okay.
But if you say like that, these are the people who propose them. They are very intelligent physicists and cosmologists. They say, how can you do that? Have you listened to my case first? I will show you the equation that will say this is possible. So, in other words, in order to escape from fine-tuning, they're saying this is alternative multiverse. But how can there be a multiverse? I'll just consider only two possibilities. The two main possibilities are, one is called the inflationary cosmology. Inflationary cosmology, and then the other one is string theory. And actually, you do combine them eventually in the end.
Okay.
What is inflationary cosmology? This was actually pioneered by Alan Guth, GUTH, if I remember, from MIT, 1984, around the time when I read it. Inflation means inflating lah. We know the universe is expanding. So the suggestion is, at the very beginning of the Big Bang, there is this inflation field called inflaton. It's an inflaton field. And this inflaton field somehow has the energy to generate the outward pressure that causes the universe to expand. Not only that, it explains, there's a expansion on steroids. Within a short, tiny time, it expanded by 10 to the power of 60 times the size. And then it stops.
Okay.
And it stops, and then the rest of the time, space-time, the universe expands, cruises along. But at the same time, you have periodic or called eternal chaotic inflation. There is another inflation, like we have a balloon expanding, and then suddenly you got pocket balloons expanding, which in time cut off, and so you have all this pocket of bubble universes. So that is what you call inflationary cosmology.
These are all from mathematical equation, right?
Well, you have to know how. I will also explain how do these mathematical equations come along. Okay, I guess I have no choice but to bring this up a little bit. But just to say, these are very sophisticated physics, the most difficult mathematics you can talk about. But it doesn't mean to say that they get a free ride. If I may use a skeptic against an unbeliever against an unbeliever, Sean Carroll, Seancarroll,
These, right?
He was actually from Caltech, like MIT Caltech. I think he's moved out from Caltech and now joined Johns Hopkins. He was one of the better debaters against William Craig. Over the universe. So he and another guy called Hewlett Tam, must be Chinaman, says that when we talk about inflationary cosmology, realistically, the chances of even this cosmology with all these eternal chaotic bubble pocket universes, the chances of them generating life-friendly universes is so small, it's 1 over 10 to the power of 66 million. When you talk about like 10 to the power of 80 would be the number of atoms in the universe. This 1 over 10 to the power of 66 million. This is an exceedingly small fraction. And if you look about it, as the discussion on the inflationary universe and also from string theory, the production of so-called multiverses. So the point I want to say is, generation of multiverses
Yeah.
themselves must require such exceeding precise values for life to emerge, itself seems to suggest that they themselves need fine-tuning, you may want to say, But also, a theory is taken seriously if beyond the equation, it suggests possibility of testing. For example, Einstein's theory of general relativity, small equation with 10 other equations hidden inside. He says that if big objects bends the gravity field, it will also bend the path of light. Then we should be able to see how, and so Eddington and some other scientists managed to devise ingenious experience to see how light seems to, in the solar eclipse, he can detect the position of the planet seems to have shifted, because meaning the light has been bent through the gravity field, So you can propose an experiment to test it. But in the inflationary universe, it does explain some things okay, but in complicated ways. But generally, if I believe in inflationary cosmology, there's a cosmic background variation, and the temperature ought to vary. But so far, all the measurements have not confirmed this wonderful idea called inflationary.
So meaning there is a mathematical equation for this, but there is no empirical or observable data to disconfirm it or confirm it, right?
How the scientists come about it is this. Now I have to go back a little bit of science. I hope the viewer will bear with me. I try to avoid all those big things. What happens is, in physics, you have large scale calculations of the universe. You depend on Einstein's theory of general relativity, and it has been confirmed a lot. It's not a complete theory, but that's how science operates. It has so far been very good. Then, but when you try to scale down to the super microscopic at the atomic level, quantum mechanics come in. Quantum mechanics is a totally different set of mechanics. For example, it began by saying that, how do I describe the probability of an electron? It's called, we have this Schrodinger equation, where your psi function, psi square, will give you the probability. When in my varsity days, we spent one whole term just to derive the Schrodinger equation, which is found. The Schrodinger equation is a wave equation, and the behavior of the waves and some calculations will give you the probable position of the electron within the electron field. So now what happens is, these two are contradictory one another. So, but at some point in the 80s, the scientists decided to merge them together. There's this. So if only I can merge Einstein equation, large scale universe, with the quantum equation, then I can make predictions. So this famous Wheeler-DeWitt equation, Wheeler DEWITT, would combine these two equations, and then now you can do equations. So you construct, basically in short, you construct a universal wave function. So that now, whereas in quantum mechanics you only calculate the probability of the electron, now with the universal wave equation, you can calculate the probability of different possible universes by changing some constant value like gravitational fields, and then you change the gravitational fields, and then you calculate the time dependence at the time to 10 to the power minus 43 seconds, because it has to be at that short period. So that then, what they call the Planck constant, then the quantum effects will take place. So, whereas we solved the Schrodinger equation decades ago, matter of fact, now you just solve the Wheeler-DeWitt equation, and you will get the probability of the universe, and that allows you for many solutions. In what they call in the equation, you solve what they call the path integral. It allows an infinite number of solutions. That's the problem. When we solve mathematical equation, an infinite number of solutions means something is not right with the equation. But here they say, the infinite number of possibilities means that there's only not this. That's the last time when you solved the quadratic equation, you got two values. One value is correct, the other value is just ignore it. I said, why ignore? It's not in real life. But now this quantum cosmology says the infinite solutions, each solution corresponds to a real universe. Now, this is a strange assertion, I must say. This is the Everett multiverse hypothesis. And so in that case, they just take it as this one solution, meaning one universe. This is just quite a very questionable assumption, you might want to say. Okay. So, what's my problem with this? The problem with this is that two things. In the mathematics, infinite solution means something is a problem. Philosophically, we say this violates the Occam principle, where entities' solution must not be multiplied endlessly. The simplest solution is likely to be the real answer. Secondly, quantum equation is just an equation. Quantum cosmological equation is just an equation. Equation is just an abstraction. When we do physics calculation, and we always ask this thing: what are the initial conditions? What are the boundary conditions? All equations are useless unless you have real initial conditions and then boundary conditions, and then we do all the calculations. But here, equation doesn't mean anything. What they do is they just play along with the equation and just say, oh, this equation must be another universe. So Stephen Hawking himself famously asked this question: what is it that breathes fire into the equation and makes a universe for them to describe?
Stephen Hawking?
Stephen Hawking. Okay. So in other words, he recognizes there's a problem. Although at the end of his life, he was still in the 80s.
Okay.
So basically, then the other thing is this: the equations, you see, the multiverse people got it the other way around. Meaning, for the equations, we get the universe. But in real life, it's not like that. The equations apply to an existing universe. You put the inflaton field calculations. The inflaton field calculation is describing a universe that is in existence. It is not creating a universe out of impossibilities. So I think there is an issue there. I will add one more issue. Part of the reason for the emergence of multiverse theory, apart from fine-tuning, is that in Stephen Hawking's calculation, Roger Penrose, if the universe is expanding, you project it backwards, it goes to a final point, Big Bang, singularity. They wanted to avoid that. Stephen Hawking avoids that by postulating imaginary time calculation, which is another story. But it's also to avoid the Big Bang and say, if you have endless popping up of multiverse, there is no question of time. It's just happening all the time. They want to avoid the Big Bang, which suggests somebody started it. But there is a famous theory, Borde-Guth-Willinghn, B-O-R-D-E, G-U-T-H, Willinghn, V-I-L-E-N-K-N. In his book, I think One World, Multiverse. Okay, I will check the title, sorry. They did this quite straightforward, ingenious, thought experiment. That if you project time backwards, how can you receive light from the back? What happened is, they came to the interesting conclusion: regardless of how many universes you're talking about, how many the theorem can deduce any number of universes that on average has been expanding throughout history, it cannot have an infinite past. Even on the quantum cosmology calculations, the universes that is reasonably expanding, they all must have a past space-time boundary. In other words, multiverses themselves
also have a beginning.
They inescapably must have a beginning.